Hi everyone. As the final topic for this week, we introduced two important probabilistic regularities in large samples, which will help us quantify the uncertainty of our data analysis. And I always want to kind of reiterate why we're going through all these probability theory concepts and through all this math is ultimately to get back to the question that we raised multiple times throughout the semester, where we looked at, differences between means, or we looked at regression coefficients, and the question was how large are these differences? To what extent are these differences really meaningful? To what extent are they different from or can we distinguish them from random noise and things like that, right? So we went through a lot of conceptual theoretical math, but ultimately what it boils down to is we need all these concepts and we need these distributions in order to make statements about the underlying uncertainty, right? In order to be able to distinguish systematic differences from just random noise, and this is what this is all about. In this last video, we will discuss two major large sample or asymptotic theorems. First, the law of large numbers, and then the central limit theorem. Okay. So the law of large numbers states that as the sample size increases, the sample average of a random variable approaches to its expected value or population average, right? So suppose we have that we obtain a random sample of n IID, so identically independent and identically distributed observations x1 through xn from a probability distribution with the expectation e of x. Then the law of large numbers states that the average of those xn's, which is equal to 1 divided by n, so of the sum from 1 equals 1 through n of xi, so all the individual x's summed and divided by the number of x's, approaches the expectation of x, right? So as or it converges to the expectation of x. So as the sample size approaches infinity, our sample mean converges to the expectation of x, the expectation of the population average. Okay. So the examples are, for example, flipping a coin 10 times and count the number of heads, and now we're interested in the probability of observing a certain number of or we're looking at the expectation in the number of heads for those 10 coin tosses, and the idea is if we repeat this many times and compute the sample mean, ultimately as we increase the sample size to infinity, we will approach the true population average. Okay, and that's all that the law of large numbers ultimately states. Okay. To kind of visualize this, we can kind of simulate this example with R and kind of look how this convergence actually occurs. Okay, and there's quite a bit of code. I'm going to walk through it step by step, right? And it's also discussed, this is taken from the book, so you can kind of follow the description in the book as well. Suppose here we're taking 100 simulations, so we're increasing our sample size to 100. Of course, you could do this with larger numbers, but in order to see this convergence, we'll go up to basically 100 simulations. Okay. For each sample size, basically up to 100, we look at 3 separate simulations where we take random draws from a binomial distribution. So that's why we have our binom with sims, so 100 simulations with p is equal to 0.2, so that's our success probability, and size is equal to 10. So we have 10 coin tosses with a probability of heads of 0.2, and we flip the coin 10 times and we repeat this process 100 times. Okay, so that's the basic setup for our random draws from these binomial distributions. We do this 3 times and kind of attach them to each other, so we have a matrix of 3 by 100. Okay. We do this not only for a binomial distribution but also for a uniform distribution, where we just take random draws from a uniform distribution, again 100 times, in three separate kind of simulations to see different scenarios play out, essentially. Okay. And then we take our average of the binomial distribution, and what we're going to do is we're going to go through this step by step. First, computing the average just of the first sample, so to speak, then adding 2 observations, 3 observations, and so on, up to 100 observations. And we're going to observe how, by increasing the sample size and by increasing the number of simulations that we're including in our average, we're approaching this true population mean. The true population mean for the binomial is, of course, this 0.2 times 10, so that's basically on average seeing two heads, and for the random, this is the uniform distribution between 0 and 1, so that's 0.5 essentially. Okay. And then we will plot this both for the binomial and for the uniform distribution. For the average, we're summing this up and we're dividing by the number of simulations, of course. Okay. But in each case, so this is ranging from 1 through 100. Okay. And then we're creating 2 separate plots where we plot as a line plot the average of these binomial distributions for the binomial, ranging from a sample size from 0 or from 1 essentially to 100, and we do the same for the uniform distribution. Okay. And this is what we see. The line, of course, shows how the average changes as we increase our sample size, right? As we move with the sample size from 0 to 100. The true population mean is, of course, 2, as I said. That's 0.2 times 10. That's n times p for the expectation of a binomial distribution, and 0.5 for the uniform distribution. And we see that at the beginning, with a small sample size, there's still a deviation between the sample mean and the true population mean. But as we increase our sample size, this becomes closer and closer, or converges to the true population average. And that's what the law of large numbers essentially describes. Okay. So as we increase our sample mean, the law of large numbers states that we get closer and closer to our population average. Okay. Excuse me. Next, we will discuss the central limit theorem. So before the law of large numbers that I just showed you, it's very useful, and we use it for important results in probability theory and statistics. But ultimately, it cannot quantify. It basically, what it tells us is that as we increase our sample size, we get closer and closer to the truth. So that's good, that's reassuring. But ultimately, it cannot really quantify how good the approximation becomes as the sample size increases, right? So there's still deviation, and we still need to quantify how large this deviation from the population, the true population value is. Okay, so we need a different tool to know how well our sample mean approximate the expectation and how much deviation there is. Okay. And this is where the central limit theorem comes in, right? So essentially, the central limit theorem. Suppose again that we obtain a random sample of n IID observations that are independent and identically distributed, x1 through xn, from a probability distribution with mean of e of x and the variance of and a given variance. Okay. Now let's denote the sample average, same as before, as x bar n, as the sum of all x's divided by n. When n is large, from the law of large numbers, we saw as n is increased to infinity, the x bar approaches the expectation of x. But now what we're saying with the central limit theorem is when n is large, then the distribution of x bar approaches a normal distribution, with the mean of the expectation of x and a variance of the variance of x divided by the sample size. Okay, So in other words, the central limit theorem tells us that the distribution of a sample mean of x bar, even if x is not normally distributed itself, and that's one of the key points, regardless of the underlying distribution of x, the distribution of the sample means x bar, according to the central limit theorem, will approximate a normal distribution, regardless, as I said, of the distribution, the underlying distribution of x. Okay. So this is the difference between the distribution of the sample average, or the sampling distribution of the mean, versus the underlying distribution of x. Okay, and that's an important kind of distinction to make here, right? Of course, the expectation of x bar is equal to the expectation of x, and the variance of this distribution, we can kind of solve this by plugging in the variance, or by plugging in the formula for x bar and solving this, and we get the 1 divided by n times the variance of x, and this is kind of the variance that we have right here. Okay. So the central limit theorem ultimately states that as the sample size increases, the distribution of the z-score for the sample mean, right? So so kind of taking into account the fact that as the sample size increases, this x bar approaches a normal distribution with the mean of e of x and the variance of and the variance equal to variance of x divided by n. We can then kind of again standardize this distribution and therefore show that the distribution of z-scores for the sample mean, so that's xn bar minus the expectation of xn bar divided by the standard deviation of x bar, that z-score then approaches a standard normal distribution, right? And that's just combining this idea of one, showing that this has a normal distribution with a given mean and variance, and then knowing that if we have a normal distribution, we can always standardize it, subtracting the average, subtracting the expectation, and dividing by the standard deviation to get to a standard normal distribution with a mean of 0 and a standard deviation of 1. And again, make sure to check out those visualizations that are linked on Canvas as well. Okay. So what does that mean? Again, we will look at a brief simulation exercise in R to kind of visualize what this actually means. Okay. What we're going to look at here is we'll look at 5,000 simulations with a sample size of 1,000, and again we're going to look at a binomial distribution and a uniform distribution. And the underlying idea here is that we want to show that even though these are not normal distributions, these are, as I said, uniform and binomial, the distributions that we introduced previously, the sample averages of those distributions still, or the distribution of sample averages still approaches a normal distribution with an appropriate, if the sample size itself is large enough, okay? And what we're going to do here is we'll write a simple loop where I ranges from 1 through 5,000. For each iteration, we take random draws from a binomial distribution. Again, 10 coin flips with a success probability of 0.2 with a sample size of 1,000. And then we compute the z-score by subtracting the population average and dividing by the variance divided by the sample size. And we do the same for the uniform distribution. We take random draws from the uniform distribution. That's a standard uniform between 0 and 1 for a sample size of 1,000, and then we z-score this sample average. Okay, so we take the average of these two random draws, subtract the true population average, and divide by the standard deviation. Okay, and then what we're going to look at is histograms of the z-scores of this sample averages. Okay, and we're going to do this separately for the binomial distribution as well as the uniform distribution. Okay, and there's a little bit more here. You can check out the code in our Studio Cloud as well if you kind of want to follow through with this. Okay, and this is basically the essence of the central limit theorem. Basically in one or two plots, so to speak. We have two underlying distributions that are not normal. We have the binomial distribution and the uniform distribution, right? One is discrete and one is uniform. One is continuous, right? And the important insight from the central limit theorem, right, is even if the underlying random variables are, in this case, binomial and discrete or uniform, when we look at the sample average, so we take a sample of 1,000 observations and we compute the average, right? And then look at the sampling distribution of that average, which means looking at how under repeated sampling we would have different basically values for that sample average. Right? We repeat the procedure, in our case 5,000 times, and take 5,000 sample averages. Right? So we have 5,000 averages across our sample, and then look at the distribution across the sampling distributions of those averages. Then the sampling distribution approaches a normal distribution regardless of the underlying distribution of x itself, right? And that's the big distinction. And I know it's hard to kind of wrap your head around what is going on here between the sampling distribution and the underlying distribution of the random variable, but that's the key distinction. You have on the one hand the random variable itself, which follows a given distribution like binomial or uniform, and then you have the sampling distribution of the average, and that's the distribution not of the random variable itself, but it's the distribution of the sample average if you repeated the sampling procedure again and again and again, right? So here we have 5,000 repeated procedures, and each of those 5,000 iterations we take a sample of 1,000 draws from the binomial or draws from the uniform, and for each of those samples of 1,000 we compute the mean, and then we look at the distribution of the sample means, right? We look at the distribution of 5,000 sample means, and that distribution of 5,000 sample means, that distribution follows a normal distribution according to the central limit theorem. And that is fundamental for us to ultimately quantify the uncertainty around our estimates when it comes to differences in means or regression coefficients. I have another quick example of kind of a special case of the central limit theorem that kind of follows the same logic, which is approximating the binomial distribution using a normal distribution. And so this is kind of another illustration of the central limit theorem at work, which is if our n is sufficiently large, so the number of draws from a binomial distribution is sufficiently large, we can use the normal distribution as an approximation of the binomial distribution. And this can be useful when making calculations by hand using the binomial distributions, because large n calculations of a binomial can be pretty tedious and also result in very large, potentially very large combinations. The n choose k component of the binomial distribution, right? But the important thing to recognize is that the binomial random variable is a sum of n IID Bernoulli random variables, and as such can be thought of as can be conceptualized the same way as we conceptualize the sum of random variables for the central limit theorem. Okay. So let's, for example, consider the following example. We have a binomial distribution with the success probability of 0.75, and n is equal to 20, right? So that means we have 20 coin flips, and this probability of heads is equal to 0.75, right? We can, based on that, we can compute the mean, which is just, if you go back to that video, the expectation of a binomial is just n times p, so that's 20 times 0.75, and the standard deviation of that binomial is n times p times 1 minus p, okay? And we can plot now both distributions, basically plot a binomial distribution with n equal 20, p equal 75, and the resulting averages and standard deviations, as well as the normal distribution for the same range of axes with the mean of mu and a standard deviation that we computed, okay? And this is what we're doing here. We're plotting both the binomial distribution, which is essentially the probability mass function for that binomial distribution, and the probability density function for a normal distribution, with a respective mean of mu and the standard deviation that we computed previously, again in the range between 1 and 20, okay? And if we do that, we see that this convergent, we see that the normal distribution can be used as an approximation of this binomial distribution. The red line here is the normal distribution, and the black bars are the actual probability mass function for the binomial distribution. And we see that these lines are actually quite close to each other. As we increase n, as we increase the number of trials in this binomial distribution, this becomes closer and closer to the actual normal distribution. And so this is kind of this approximation of the binomial distribution using the normal distribution is essentially a special case of the central limit theorem, if we kind of conceptualize the binomial distribution as a sum of n IID Bernoulli random variables, right? So the same kind of argument is the same underlying mechanism is ultimately going on here. It's approximating or approaching a normal distribution, essentially. All right. So this is all for this week. I know these are lots and lots of videos and lots of concepts. So I'm looking forward to our Q&A session where we can kind of go back to some of the questions and revisit some of that material in more detail. But other than that, I'm looking forward to our next discussion next week.